Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a really interesting paper called ZebraLogic on the scaling limits of LLMs for logical reasoning. Anyone have initial thoughts after reading it?
Yeah, I found it pretty fascinating, if a little concerning. It really throws a wrench in the idea that just scaling up large language models is the guaranteed path to AGI. It suggests that we might be hitting a wall, at least when it comes to logical reasoning.
Concerning is an understatement. I've been saying for ages that just throwing more data and parameters at these things isn't going to magically create intelligence. This paper seems to be providing some pretty solid evidence to back that up. I mean, they show clear limitations even with increased scale, right?
Right, and the way I see it, it confirms my suspicion that current deep learning is a glorified form of brute force pattern matching. It's impressive, sure, but it's fundamentally limited. We need to rethink the core algorithms, not just scale the existing ones.
Okay, so for our listeners, the ZebraLogic paper essentially investigates how well large language models perform on logical reasoning tasks as they get bigger. What they found is that, beyond a certain point, simply increasing the size of the model doesn't necessarily improve its ability to solve logical problems. In some cases, it even gets worse. What does that mean for the field?
Well, it means that my dream of a purely data-driven AGI might need some tweaking. I still believe that deep learning is a powerful tool, but maybe it needs to be supplemented with other approaches. Think about it. These models are trained on vast amounts of text data, but that data doesn't necessarily contain explicit logical rules. They're learning correlations, not necessarily causation or logical inference.
Exactly. And that's where I think neuro-symbolic approaches come in. We need to find ways to integrate symbolic representations of knowledge into these models so they can actually reason about the world in a more structured way. I mean, humans don't just memorize patterns. We build mental models and use logic to make inferences.
That's a great point, Donald. The spatiotemporal aspect is often overlooked. So, Sarah, can you give us a concrete example of how a neuro-symbolic approach might work in practice to address these limitations?
Sure. Imagine a task that requires understanding spatial relationships, like the blue cube is to the left of the red sphere, and the red sphere is behind the green pyramid. Which object is furthest back? A purely deep learning model might struggle with this because it's relying on statistical associations between words and images. A neuro-symbolic approach, on the other hand, could represent these objects and their relationships symbolically. It could then use logical rules to infer the answer. If A is left of B and B is behind C, then C is furthest back. We can build hybrid architectures where the neural network extracts features from the images and the symbolic system reasons about those features.
Okay, I see what you're saying. So, the neural network acts as a kind of perception module, and the symbolic system does the heavy lifting in terms of reasoning. But wouldn't that require a lot of hand engineering of rules and symbols? Isn't the beauty of deep learning that it can learn these things automatically from data?
That's the challenge, right? We don't want to go back to the old days of expert systems where everything is hard-coded. The goal is to find ways to learn the symbolic representations and rules from data as well. There are techniques like neural program synthesis and differentiable reasoning that try to do just that. The network will try to write a program that solves the problem. It doesn't always work, but it's an approach.
But even if you can learn the rules, how do you ensure that the system can generalize to new situations? If the system is trained on a specific set of objects and relationships, will it be able to handle novel objects or more complex spatial arrangements? That is where the spatiotemporal aspect becomes even more critical. The system needs to be able to understand the underlying geometry of the world, not just memorize specific examples.
So, Donald, how would you approach that problem of generalization and spatiotemporal reasoning? What kind of algorithmic changes are you envisioning?
Well, I think we need to move away from treating space and time as just another set of features to be learned. We need to build algorithms that explicitly represent spatiotemporal relationships and can translate between different coordinate representations. Imagine a robot navigating a room. It needs to be able to integrate information from its sensors, for example, cameras, LiDAR, and create a 3D map of the environment. It also needs to be able to reason about how objects are moving in that environment. This requires a core algorithm that can handle different coordinate systems, Cartesian, polar, etc., and can transform information between them. Then you can combine the neural networks with this spatiotemporal approach.
That sounds incredibly complex. Are there any existing AI systems that are tackling this problem of spatiotemporal reasoning in a meaningful way?
There are some promising developments in areas like robotic navigation and autonomous driving. These systems often use techniques like simultaneous localization and mapping, SLAM, to build maps of their environment and track their own position. However, these systems are still quite specialized and don't necessarily generalize to more abstract forms of reasoning.
And that's the key, isn't it? We need to find ways to bridge the gap between perception and reasoning, between concrete sensory experiences and abstract thought. I think that's where the neuroscientific insights come in. How does the brain represent space and time? How does it integrate information from different sensory modalities? If we can understand these mechanisms, we can start to build more biologically inspired AI systems.
Absolutely, and that's something I've been thinking a lot about lately. Neuroscientific studies of the hippocampus and prefrontal cortex, for example, suggest that these brain regions play a critical role in spatial navigation and working memory, respectively. Could we draw inspiration from these structures to build AI architectures that exhibit more nuanced logical reasoning abilities? For example, can we map logical representations onto specific neural populations or synaptic connections?
That's fascinating. So you're suggesting that we could literally build AI systems that mimic the brain's architecture? But wouldn't that be incredibly difficult? The brain is so complex, and we still don't fully understand how it works.
It's definitely a long-term goal, but I think we can start by focusing on specific cognitive functions and trying to reverse engineer the neural circuits that underlie those functions. Even a simplified model of a brain region could provide valuable insights into how to build more intelligent machines. If we can understand how neuronal oscillations and synchronicity facilitate information processing, we may have a major leap forward in AI.
Yeah, and I think it's important to remember that we don't necessarily need to replicate the brain exactly. We just need to understand the underlying principles. Think about the Wright brothers. They didn't build a plane that flapped its wings like a bird, but they did understand the principles of aerodynamics.
That's a great analogy, Sarah. We need to focus on the underlying principles of spatiotemporal reasoning and build algorithms that embody those principles, even if they don't look exactly like the brain. If we can map the principles of the brain, this could lead to emergent properties that are not available currently.
Okay, so let's say we can develop these more biologically inspired algorithms. How would we actually test them? What kind of benchmarks would be appropriate for evaluating their performance on logical reasoning tasks?
That's a crucial question. The benchmarks used in the ZebraLogic paper are a good starting point, but we need to develop more challenging and realistic tasks. We need to move beyond simple logical puzzles and start testing these systems on tasks that require integrating information from multiple sources, dealing with uncertainty, and reasoning about the physical world.
And we need to make sure that the benchmarks are spatiotemporally grounded. We could, for example, create virtual environments where AI agents have to navigate and interact with objects in a realistic way. The agents would have to solve problems that require understanding spatial relationships, predicting future events, and planning actions over time.
That's a great idea. We could also draw inspiration from developmental psychology. We could design tasks that mimic the way children learn about the world and see how well our AI systems perform on those tasks. The AI could learn to sort objects into piles, then learn which ones are on the right or left side of something else.
So, it sounds like we all agree that the ZebraLogic paper highlights a critical limitation in current LMs and that we need to explore new approaches to achieve true AGI. But what are the specific research directions that we should be focusing on in the near future?
From my perspective, the most promising direction is the development of neuro-symbolic architectures that can seamlessly integrate neural networks with symbolic reasoning systems. We need to find ways to learn symbolic representations and rules from data and to build systems that can reason about the world in a more structured and explainable way. I also think that we have to revisit the training paradigm. Current deep learning models are trained on unstructured data from the internet, which may lead to hallucination.
I think the key is to focus on developing core algorithms that can explicitly represent spatiotemporal relationships and translate between different coordinate representations. We need to move beyond brute force pattern matching and build systems that can truly understand the geometry of the world. We also need to think about the hardware that we're using. Current computers are not well suited for spatiotemporal reasoning. We need to explore new hardware architectures that can more efficiently process this type of information.
I still believe that scaling up deep learning models is a viable path to AGI, but I also recognize the need for new approaches. I think we should be exploring ways to augment LLMs with symbolic reasoning capabilities and to develop new training techniques that can improve their ability to handle logical reasoning tasks. And we need more data, specifically data that is curated and designed to test the logical capabilities of the model. If we can create data that tests specific logical skills, then we can see if the model improves.
And from my perspective, the most exciting research direction is the integration of neuroscientific insights into AI. We need to study the brain to understand how it represents knowledge, reasons about the world, and learns new skills. We can then use this knowledge to build more biologically inspired AI systems that are more robust, adaptable, and intelligent. Also, the democratization of knowledge is also something that could help stimulate progress. Removing barriers to entry could bring new ideas to the table.
That's a great point about democratization. The more people working on this, the better. We need all the brain power we can get.
Well, this has been a fascinating discussion. It's clear that the path to AGI is not as straightforward as we once thought, but there are many exciting research directions to explore. Thanks for sharing your insights.
Thanks for having me. It's always good to challenge our assumptions and think critically about the future of AI.
My pleasure. I'm looking forward to seeing what the next few years bring.
Definitely. The journey to AGI is going to be a wild ride.
And that's all the time we have for today. Join us next time on Cognitive Spirals as we delve into another fascinating topic in the world of AI and neuroscience.